Welcome to this explainer. Today, we're diving straight into the engine room of modern system design to decode what actually happens inside an API gateway.
What really happens when a request enters a gateway? If you're prepping for a back-end interview, you absolutely need to nail this. But first, let's visualize the problem.
Imagine a mobile client frantically calling 50 different microservices. Communicating directly like this creates an unmanageable, chaotic web of crisscrossing dependencies. It's a complete nightmare.
Enter the API gateway. It acts as a single, unified entry point, abstracting away all that back-end complexity and transforming chaos into a clean, elegant facade. In an interview, you might be asked, wait, isn't that just a load balancer? Not quite. A load balancer distributes traffic blindly at layer 4. An API gateway operates at layer 7, intelligently reading the actual business context of your requests.
Let's ride along with a single client request and see exactly what's going on under the hood.
The journey kicks off the moment a client request packet is fired, traveling right up to the gateway's front door.
The very first stop is the security checkpoint. The gateway verifies the user's identity right here at the edge, so your internal microservices don't have to.
It grabs the authorization header and cryptographically validates the JSON web token.
Specifically, it checks the EXP claim to ensure the token hasn't expired, verifies the trusted issuer via the ISS claim, and confirms the correct audience using the AUD claim.
Okay, we're authenticated, but we must act fast to protect the backend from getting completely overwhelmed.
The request hits the rate limiter. Gateways often use a token bucket algorithm here, where every incoming request consumes a token just to pass through. If that bucket is empty, the gateway immediately rejects the excess call, throwing a 429 too many requests error.
Assuming our packet survived rate limiting, where does it go next?
Next up is routing. The gateway reads the request's URL path and runs it against dynamic routing rules to figure out the target service.
But there's a catch. In a dynamic cloud environment, microservice IP addresses change constantly. It's a moving target.
To find the live instance, the gateway queries a service registry, discovering the exact current location of the microservice we actually need. Armed with that correct IP address, the gateway forwards the payload and our request finally reaches its destination.
Now, to prevent the gateway itself from becoming the bottleneck, we have to scale it up.
We place a layer 4 load balancer in front to distribute incoming traffic across multiple stateless gateway instances, ensuring absolute high availability. And if a downstream service crashes, the gateway uses a circuit breaker pattern to fail fast. It instantly blocks traffic, preventing cascading system failures.
So if you're ever asked in an interview why we really need API gateways,
The answer is clear. They abstract complexity into a unified entry point, centralize security, manage traffic spikes, and entirely decouple your clients from your internal architecture.
Now that you know the exact journey of a request, how will you architect the gateway for your next backend system? Are your microservices exposed, or are they protected?